All right, so we are on to the next idea of the day. We're going to talk about proving things using something called mathematical induction. And if I try to describe it without giving you an example just right off the bat, it's going to be a disaster. So, mathematical induction is the following process. We are attempting to prove that 1 plus 2 plus 3 plus 4 plus so on plus n. So what we're really saying here is that the sum of the first n positive integers is equal to n times n plus 1 over 2. And the idea is that we're trying to prove that this works for any value of n. N can be 1, n can be 2, n can be 1,000,000, n can be 573, whatever. So, we're going to do this in 2 steps. Step 1, show it's true for n equals 1. We're going to show that it's true for the lowest possible value of n. Okay. Step 2 has kind of 2 parts, so it's step 2a. Assume it's true for some value k. For some value n equals k, and yes, I understand that we're introducing another letter there, and that's confusing, but we're saying, all right, it's true for some k. Now, we've already, hopefully at this point, we've already proven it's true for n equals 1, so there's the thing that we've proven it for, but we're assuming that it's true for some value k, and then use that to prove the statement is true for k plus 1. Okay, so I understand this is really vague, it sounds weird, it's very easy to be like, what on earth is going on here? But let's do it. So, step 1 in this very problem. So we are trying to prove that, this thing is true. So step 1, if n equals 1, the first n integers, of course, add to 1. And a lot of times this first step feels trivial, so that's good. It feels like almost too obvious. So this is the first n integers add to 1, and does this in fact equal 1 times 1 plus 1 over 2? Because remember, we're trying to prove that it is equal to this thing, and we're using n equals 1. Well, of course that's true. 1, of course, equals 1 times 2 divided by 2. That's just obviously true. We got this. So step 1 is done. We have proved it. So what we do there, sorry, I know that probably looks really strange. So step 2, part A, we're going to assume, assume 1 plus 2 plus ... plus k works, so that this in fact equals k times k plus 1 over 2. We get to assume this. This is an assumption, but that's okay. In fact, it's got a name. It's called our inductive hypothesis. So then we need to show that 1 plus 2 plus ... plus k plus 1, because we're going all the way out to k plus 1 now, is equal to k plus 1 multiplied by k plus 1 over 2. We need to show that this thing is equal to, we can simplify this a little bit, k plus 1 multiplied by k plus 2 over 2. Okay, we need to show this. We haven't done it yet. So we're going to do that over here, but I'm going to put it next to this inductive hypothesis because this is going to show up. So let's take this 1 plus, let's undo that. I don't like that color. So we're going to do 1 plus 2 plus dot, 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 plus k plus 1. And we're going to note that this thing, 1 plus 2 plus dot, dot, dot to k, is k times k plus 1 over 2. Because we have assumed this. This is our inductive hypothesis, so we're going to assume this for the moment. And then we're realizing, okay, that's plus k plus 1. This is the thing we're actually working with. Now we want common denominators here, so we're going to make them. So this is k times k plus 1 over 2 plus 2 parentheses k plus 1 over 2. So it's going to get us k times k plus 1 plus 2 times k plus 1, all divided by 2. And I could have multiplied the k's out, but I decided not to. And now, notice we have a k plus 1 here and a k plus 1 here. So we are factoring out a parenthesis, which, if you remember factoring by grouping, might be familiar, but if not, you might have forgotten this, but we're going to factor out a k plus 1. And we factor out a k plus 1 from this term, leaving you with a k, and a k plus 1 from this term, leaving you with a 2. And so this numerator is now k plus 1 times k plus 2, which is equal to 2, which, if worked out, it's right next to it, is the thing we were trying to show. That's what we were trying to show. And so we've actually proven it, which you'll be able to do, and I'm going to recap this because I understand why it might not make a ton of sense. We can actually say that so we'll say, therefore, we've proven that 1 plus 2 plus 3 plus da 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 plus n is equal to n times n plus 1 over 2 by mathematical induction. All right, so what happened here? What's happening here is we're proving that it's true at least once. That's what we do in step 1. We're proving that this statement is true at least for some value of n. And in this case, we're going to start with it's true for a value of n equals 1. And then what step 2 is saying is, okay, well, if it's true for some value, is it then true for the next one, right? So if it's true for k, is it then true for k plus 1? And we assume that it's true for k, and what happens is if it's true for k, then just basic mathematical identities lead us to this fact that it also is true for k plus 1. Because the first k plus 1 integers are just this top line right here. We notice that these first k terms, based on our assumption, are equal to this thing. And then we just do a little bit of rearranging and realize that we get to here. This k plus 1 times k plus 2 all divided by 2, which is what we would hope to find if it was true for the next term, the k plus 1th term. And therefore, we know it's true for the first term, we know it's true for n equals 1, and for any value of n it's true for the next one, for that value plus 1. So therefore, it must be true for n equals 2. And if it's true for n equals 2, well, it's got to be true for the next one. So it's true for n equals 3. If it's true for n equals 3, it's got to be true for the next one. So it's true for n equals 4, and so on. And that just kind of dominoes all the way to infinity. And so therefore, it is true for any value of n. and that is proving something by mathematical induction, and we've done it. We'll do other examples. We'll do them next because I imagine you're looking at that and going, yikes, wow, I don't know how to do this. So we'll do it again. First time you see this is always confusing, but let's see it a few more times.